Hi, ma'am. This is T. Kushi from ITA, and my roll number is 37. And my topic of concept video for the subject ADE is operation of full wave rectifier. So let us know about the introduction. Electric circuits that converts AC to DC are known as rectifiers. Rectifiers are classified into two types, that is half wave rectifiers and full wave rectifiers. So here converting from AC to DC means converting from alternating currents to direct currents. So rectifiers are classified into two types. One is half wave rectifier, the other is full wave rectifier. Significant power is lost while using a half wave rectifier and is not feasible for applications that need a smooth and steady supply. For a more smooth and steady supply, we use a full wave rectifiers. So let us know what is a full wave rectifier. A full wave rectifier is defined as a rectifier that converts the complete cycle of alternating current into pulsating DC. Unlike half wave rectifiers that utilize only the half wave of the input AC cycle, full wave rectifiers utilize the full cycle. The lower efficiency of the half wave rectifier can be overcome by the full wave rectifier. So, generally, the basic definition of a full wave rectifier is that converting the AC signal, that is alternating current signal, into DC signal, into pulsating DC signal. So, generally, as you all know, in half wave rectifier, we'll only use half cycles, that is only positive cycles are considered and negative cycles are not considered. So whereas in a full wave rectifier it is not like that. You are going to consider both positive half cycles as well as negative half cycles. So in this way you will come over the low efficiency. Generally half wave rectifiers are generally very low efficient. So to overcome that problem we are going to use the full wave rectifiers. So let us know about the full wave rectifier circuits. The circuit of the full wave rectifier can be constructed in two ways. The first method uses a center tapped transformer and two diodes. This arrangement is known as center tapped full wave rectifier. And the second method uses a standard transformer with four diodes arranged as a bridge. So this is known as bridge rectifier. So from this slide, you can understand that there are two types of full wave rectifiers. The first one is center tap full wave rectifier and the second one is full wave bridge rectifier. So let us know about both of them in a clear way. So coming to center tap full wave rectifier. The circuit of center tap full wave rectifier consists of the following main components. It consists of two diodes, a center tapped transformer and a load resistance. So you can see in the picture shown, you'll have an AC supply, you'll have a transformer, you are having two diodes named D1 and D2, and you are having a load resistance as mentioned, as shown in the figure. So these three are the main components of center tapped full wave rectifier. So now let us see the working of center tapped full wave rectifier. The circuit of the full wave rectifier consists of a step down transformer and two diodes that are connected and center tapped. The output voltage is obtained across the connected load resistor. The input AC supplied to the full wave rectifier is very high. The step down transformer in the rectifier circuit converts the high voltage AC into a low voltage AC. The anode of the center tap diodes is connected to the transformer, secondary winding, and connected to the load resistor. During the positive half cycle of the alternating current, the top of the secondary winding becomes positive, while the second half of the secondary winding becomes negative. So generally in full wave rectifier, we are going to use step down transformers. Generally, whatever the AC supply which is being supplied is very high. It is having high voltages. So the first step is to convert that high voltage to low voltage. So this work is done using the step down transformer. So the step down transformer helps to convert high voltage AC supply signal to a low voltage AC supply signal. And then after this conversion, the next procedure takes place and it is converted into DC signal. So coming to the positive half cycle, during the positive half cycle of input AC voltage, the end A of the secondary winding becomes the positive and the end B becomes the negative end. This makes the diode D1 forward bias, that is, it acts as a closed switch, and diode D2 acts as a reversed bias, so it acts as an open switch. Therefore, current flows through the load resistance RL from P to O. So as you can see in the picture, so during the positive half cycle, end A is considered as the positive end and end B is considered as the negative end. And diode D1 is forward bias, so it acts as a closed switch, and diode D2 is reverse bias, so it acts as a open switch, and the current flow of the is only through the load resistance, that is from P to O as mentioned in the figure. So coming to the negative half cycle, during the negative half cycle of input AC signal, the end B of the secondary winding becomes positive and the end A becomes negative. This makes the diode D2 forward biased and acts as closed switch, and D1 diode as reverse biased, so it acts as open switch. Therefore, the current will flow from B to O through diode D2, load RL, and lower half of the secondary winding. So coming to negative half cycle, it is completely opposite of the positive half cycle. Here now end B becomes positive end and end A becomes negative end. So diode D2 is forward biased and it acts as closed switch, and diode D1 becomes reverse biased and it acts as open switch, and there will be a current flow from B to O as shown in the figure. So when the current flows from B to O, it flows through the diode D2, it flows through the load resistance and in the lower half of the secondary winding. So this is a complete diagram of center tap full wave rectifier. Input voltage is taken in this waveform and it is gone through the following conditions, and you will get the output voltage waveform in this way. So the second one is full wave bridge rectifier. So it is full wave bridge rectifier. The full wave bridge rectifier eliminates the need of center tap transformer. It contains 4 diodes connected to form bridge. The circuit of full wave bridge rectifier consists of following main components, that is 4 diodes, a step down transformer, a load resistance. So as you can see in the picture, the 4 main components of full wave bridge rectifiers are 4 diodes, a step down transformer, and a load resistance. So now let us look at the working of a full wave bridge rectifier. So here also you'll have again positive half cycle and negative half cycle. So during the positive half cycle, the end A of secondary winding becomes positive and the end B becomes negative. This makes the diodes D1 and D3 forward bias, that is acts like a closed switch, and diodes D2 and D4 are reversed bias, so that acts as a open switch. The current flows from A to B through diode D1, load RL, and diode D3. So now look at the figure. So when a positive half cycle is going on, end A will be as the positive end and end B is taken as the negative end. And diodes D1 and D3 are forward biased. So they'll act as a closed switch. Coming to diodes D2 and D4, they are reverse bias, so they'll act as an open switch. And the current flows from A to B. That means it flows through the diode D1, load resistance RL, and diode D3. Coming to the negative half cycle, as already known, negative half cycle is completely opposite of positive half cycle. So during negative half cycle, the end A of secondary winding becomes negative and end B becomes positive. This makes the diodes D1 and D3 reverse bias, so they act as open switch, and diodes D2 and D4 are forward biased, so they act as closed switch. The current flows from B to A through diode D2, load RL, and diode D4. So as you can see in the picture, so here end A becomes negative and end B becomes positive and completely reverse. So the D1 and D3 are reverse biased, so they act as open switch. D2 and D4 are forward biased, so they act as a closed switch. So here current flows from B to A, that is through diode D2, load RL, and diode D4. Therefore, the current flows through load RL in the same direction for both the cycles of input AC supply. Hence, DC output is obtained across the load. Generally, DC output is always obtained across the load. So what are the main advantages of bridge full wave bridge rectifier. The output is twice that of the center tapped full wave rectifier for the same secondary voltage, and there is no need of center tapped transformer. For same DC output, peak inverse voltage of full wave bridge rectifier is half that of the center tapped full wave rectifier. And coming to the disadvantages, it requires 4 diodes, and during each half cycle of AC input, the 2 diodes that conduct are in series, which causes voltage drop in internal resistance of diodes. So see, these are some of the advantages and disadvantages of a full wave bridge rectifier. So there are some important formulas for full wave rectifiers. First one is peak inverse voltage. Peak inverse voltage is the maximum voltage a diode can withstand in the reverse bias direction before breakdown. The peak inverse voltage of the full wave rectifier is double that of the half wave rectifier. So the peak inverse voltage across the diodes D1 and D2 is 2V max. Coming to the DC output voltage, DC output voltage is denoted by VDC. So VDC is equal to I average into RL. RL is nothing but load resistance. So VDC finally becomes VDC is equal to 2 by pi I max RL. Coming to RMS value of current. So RMS is nothing but root mean square value. So IRMS is equal to I max by root 2. So coming to form factor. So form factor is defined as the ratio of RMS value of the current to the average value of current, and it is denoted by letter KF. So KF is equal to IRMS by IDS, that is equal to I max by root 2 by 2 I max by pi. So finally it is pi by 2 root 2. So KF value is 1.11. So form factor for a full wave rectifier is 1.11. Coming to peak factor, it is denoted by symbol KP, and it is defined as a ratio of peak value of current to that of RMS value of current. So I max by root 2. So peak factor value for a full wave rectifier is root 2. Coming to rectification efficiency, it is defined as the ratio of DC output power to that of AC output power, and it is denoted by symbol neta. And the efficiency of a full wave rectifier is always 81.2%. So now let us look at the advantages of a full wave rectifier. So what are the advantages of full wave rectifier? The rectification efficiency of a full wave rectifiers is double that of a half wave rectifier. The efficiency of half wave rectifiers is 40.6%, while the rectification efficiency of a full wave rectifier is 81.2%. The ripple factor in a full wave rectifier is low, hence a simple filter is required. The value of a ripple factor in full wave rectifier is 0.48, while in a half wave rectifier it is about 1.21. And the output voltage and the output power obtained in a full wave rectifiers are higher than that obtained using half wave rectifiers. And the only disadvantage of the full wave rectifier is that they need more circuit elements than the half wave rectifiers, which makes it costlier. So in this whole presentation, we have learned about full wave rectifier, and the main difference between full wave rectifier and half wave rectifier is that in half wave rectifier, you are going to use only the positive half cycles, and the negative half cycles are wasted, so it is less efficient. Whereas when you come to a full wave rectifier, you're going to use both positive half cycles and negative half cycles. And in full wave rectifiers, you are having two types of circuits, that is center tapped full wave rectifier and bridge rectifier. So in center tapped full wave rectifier, you're going to use a step down transformer. You're going to use a center tap transformer with 2 diodes. And when you're coming to the bridge full wave bridge rectifier, you're going to use 4 diodes and a step down transformer. And then bridge rectifier, bridge full wave rectifier, there is no need of a center tapped transformer. So that is one of the main advantage. And bridge wave rectifier is more efficient when compared to center tapped full wave rectifier. And generally, rectifier is nothing but conversion of AC signal into DC signal. So the process of conversion of AC signal into DC signal is called as the rectification. So generally, the AC signal which you are giving as input is very high. So first step is to convert that high AC signal, high voltage AC signal to low voltage AC signal. So here to convert this, you're going to use a step down transformer. So in a step down transformer, the primary windings are less, whereas the secondary windings are more. So with the help of this step down transformer, first step you're going to converting the high voltage AC signal to the low voltage AC signal. After that, using either center tapped full wave rectifier method or using bridge full wave rectifier method, you're going to convert the AC supply to the DC supply. And when compared with when we compare full wave rectifier with half wave rectifier, full wave rectifier is more efficient because the efficiency of full wave rectifier is 81.2%, whereas the efficiency of a half wave rectifier is 40.6. And coming to the ripple factor also, the ripple factor of the full wave rectifier is 0.48 only, whereas when you talk about a half wave rectifier, it is 1.21. So there is a large difference. And coming to the output voltage also, in half wave rectifiers, the output voltage is very less because you're only going to consider the positive half cycles. And in full wave rectifiers, it is quite good and high because you're going to consider both positive half cycles and negative half cycles. But the only disadvantage of full wave rectifiers is that you need more elements in the circuit. So this makes the circuits a bit more costlier. So these are some of the important points. And the main point is that you'll have diodes. Some of the diodes acts as forward bias. So when it is in forward bias, then it is a closed switch. And when the diodes are in reverse bias, it is open switch. So these are other two main points which you have to remember for a full wave rectifier. So we conclude that full wave rectifiers are more efficient when compared to half wave rectifiers because they use both positive half cycles and negative half cycles, and it is more efficient and it has less ripple factor as well. So comparing all these aspects, we can say that full wave rectifiers are more efficient, more better when compared with a half wave rectifier. Hope you guys understood this presentation. Thank you so much.